Welcome, high school teachers, to Population Growth and the Logistic Map. This is a course about mathematical modelling. Mathematical modelling is when you use maths to describe something in the real world. In this course, we are going to use maths, in particular the logistic map or the exponential map, to describe things in the real world. Population growth or compound interest. Being able to describe these real world things mathematically makes you very powerful. It enables you to say what's going to happen in the future as well as what has happened in the past. And it's a great way to motivate students to want to learn mathematics, just precisely because it makes them so powerful. For this first module, we're going to talk about compound interest and the exponential map. And this underlies the more sophisticated model called the logistic map. Let us recall the formula for compound interest. The amount at time t, denoted AT. The R is the annual interest rate. N is the number of compounding intervals, for example, annual compound intervals, or monthly, which is what your banks do, or daily, which is what happens if you have credit card debt. And T is the time in years. And with these things known to us, we are able to say that an original amount, A0, times by 1 plus the annual rate appropriately scaled down by the number of compounding intervals raised to this power, which is the number of compounding intervals per year, times by the number of years, will give you the amount at time t. Let's put this compound interest formula to work. What happens to, say, $1 in 1 year compounded at a rate of 100%, and our compound interval is annually. So every year you get 100% of what was initially put in. So A0 is 1. We times this by 1 plus the rate, which is 100%, divided by the number of compounding intervals, so that's 1 divided by 1, to the power of 1. And, unsurprisingly, this is 2, which is what you might expect. So after 1 year, our $1 became $2. $2 would become $4, $4 would become $8. We are able to use this exponential model to predict what's going to happen in the future to our $1. We can also put the model in reverse and say, what has happened to get us here? I have $1 today. How much did I have this time last year? And we're able to use the model to say, well, you must have had 50 cents this time last year. So already this primitive model makes us powerful. We're able to say what happens in the future and what has happened in the past. Jacob Bernoulli in the 17th century wanted to know what happens if we compound more frequently. What happens if we compound monthly, as banks do? We can invoke the compound interest formula. It's still $1 initially, times 1 plus the rate of interest divided by the number of compounding intervals, which is 12, to the power 12. And this, happily, is equal to 2.6135. to 4 decimal places. Let's plot this on the graph. So we have now 12 compounding intervals. We still start at 1, but instead of finishing at 2, we finish at about 2.6, and then it keeps getting bigger. We can also plot this in reverse, and it's slightly below what we had previously. So our curve is we get slightly more interest. Well, actually, we get quite a bit more interest, and we get more time intervals. Surely we'll get even better when we compound daily. Unfortunately, that's not true. When you compound daily, you have 2.7146. to 4 decimal places, which is not that much better than when you compounded monthly. So if we plot that, we get a lot more time intervals, but it's not getting that much bigger than our black curve. And it goes down here, so it's slightly below the black curve over here. So there appears to be some kind of barrier to how much money we can get by compounding more and more frequently. Let's compound really frequently. In general, if I compound at n time intervals, I have 1 on n to the power n. And what happens if I take n to the max? I'm going to take the limit as n goes to infinity. This is called continuously compounding interest. It's the most frequently compounding interest we have. And the amount you get for investing $1 for 1 year and compounding all the time is 2.7182. Well, 3 rounded up to 4 decimal places. This is a very famous number. This number is also known as E, and it was Euler who first studied this number. And he studied it in this way, motivated by compound interest. This presents an alternative and more historically accurate motivation for the number E. Let's see how this number E sits with the rest of our compound interest. It's continuously compounding, so we have this solid line here, and it sits below the others over here and sits above them. And when time is equal to 1, this is equal to approximately 2.7183. So we have when time is equal to 1, it sits about here, somewhere between 2 and 3. The formulas from the previous slide generalize to an arbitrary rate of interest R. We can see that the annual rate of interest would change. So instead of 1 here, or 100%, we now have this number R. The monthly rate of interest would change. Because R is specified as an annual rate of interest, we must divide it by 12 to make it a monthly rate of interest. And we compound 12 times every year. Similarly, daily interest becomes R divided by 365, the appropriately scaled down version of annual interest, and we compound every day. For continuously compounding, something slightly different happens. Again, we have this formula where we take the limit as n gets very large of our compound interest formula. Which we can write like this. So I've rearranged R over n to make it 1 over n over R. And up here I've divided and multiplied by the rate of interest R. If I let m be equal to n over R, then this is equal to limit as m approaches infinity of 1 plus 1 over m to the power mr, which is equal to e to the r. So continuously compounding interest has this convenient form where it's expressed as a power law of e to the power r. And this goes back to the original definition of e to the x given by Euler in the 18th century. He said that e to the x, and now we're moving away from this idea of compound interest and we just have this arbitrary value x. He said that this is the limit as n goes to infinity, 1 plus x over n to the power n. This quantity e to the x is quite a useful number, but its heritage goes back to compound interest. So this is a good alternative way of motivating the study of the exponential function, the way Euler would have done it, and taking it back to its original historical roots in the world of finance. So now we see how the function e to the x behaves in comparison to the more familiar functions 2 to the x and 3 to the x. 2 to the x grows slower, still exponentially, but slower, and 3 to the x grows faster. So now we're in a position to use our model for compound interest to answer some real-world questions, such as, if I invest $1 in a bank at a rate of interest R, how long does it take until my $1 becomes $2? Well, the answer depends on the frequency at which I'm compounding my interest. If I can compound my interest continuously, then we can model the amount of money I have at time t by this. And I want my $1 to become $2. Good. This is an equation that we can solve. Let's take the log of both sides. So we have RT is equal to natural log of 2, and we can approximate the natural log of 2 by 0.7. So this is approximately equal to 0.7. And we come up with the following formula for the amount of time it takes. So the amount of time it takes for my money to double is 0.7 divided by my rate of interest R. We can see from this formula that the amount of time it takes is inversely proportional to the rate of interest R. Also, this represents a lower bound on the amount of time I have to wait to double my money. Practically speaking, if you recall the curve, all the other curves were lower than the exponential curve. So this exponential curve is going to reach 2 before any of the others. Let's apply this formula. If R equals 1, then t is equal to 0.7 divided by 1, which is 0.7 years. So this exponential function is going to reach 2 at time equals 0.7. What if I have a more realistic rate of interest? If R is equal to 0.1, so a rate of interest of 10%, then t is equal to 0.7 divided by 0.1, which is equal to 7 years. And if I have an even more realistic rate of interest, like if R is equal to 0.025%, then t is equal to 0.7 divided by 0.025, which is equal to 28 years. So far we've taken a historical approach to this function e to the x. It may not be the approach that you're familiar with, but it's the same function. It still obeys this key property here that the derivative of e to the x is still e to the x, and we'll see why. Well, if I start off with the left-hand side of this equation, d dx of e to the x, then using our historical definition, using Euler's definition of e to the x, this is equal to d dx of the limit as n approaches infinity of 1 plus x on n to the power n. Which is equal to the limit as n approaches infinity of d dx 1 plus x on n to the power n. We are now in a position to take the derivative of this. The limit stays the same. And we have n times 1 plus x over n to the n minus 1, and I have to multiply through by the derivative of this, which is 1 on n. And we can see this is the limit as n approaches infinity of 1 plus x on n to the power n divided by 1 plus x on n. And as n goes to infinity, this, again using Euler's definition, is e to the x. And this goes to 1. So we just get left with e to the x. Suppose we ask a bright high school student whether or not there exists a polynomial that satisfies this differential equation. That is, we ask, does d dx of some polynomial p of x equal p of x for some polynomial p of x? Well, let's try and answer this question. We will begin by letting p of x equal an infinite polynomial, a0 plus a1 x1 plus a2 x2 plus so on. So the a's represent a0 is the coefficient of x to the 0, an is the coefficient of x to the n. Well, if this differential equation is satisfied, then this is equal to d dx of p of x, which is equal to, well, this, the derivative of this becomes a1 plus twice a2x plus x to the 1 plus 3a3x squared plus so on. All these coefficients shifted to the left and they picked up the power of x they were next to. And now we can compare coefficients. a1 is a0. 2a2 is equal to a1. So 2a2 is equal to a1, which is also equal to a0. 3a3 is equal to a2. And so on. So a1 equals a0, a2 is half a1, which is half a0, a3 is equal to 1/3 a2, which is 1 on, I'll write this as 3 factorial a0. And in general, an is equal to 1 on n factorial a0. So our polynomial equals a0, I'll just factor out a0, 1 plus x squared on 2 factorial plus x3 on 3 factorial plus and so on. So our polynomial is a scalar multiple of this infinite polynomial. And this infinite polynomial is an alternative representation of this e to the x, going back to Euler. This is what's called a power series representation of e to the x. It's very useful. This is what calculators use to calculate the value of e to the x for an arbitrary value of x.